Hello, my name is Kadus Telexo. This is my presentation for my final project for Introduction to Deep Learning. My project is classifying optical coherence tomography or OCT imagery. So a little introduction. Deep learning in recent years has shown promise in medical diagnostics. This is because of increase in computational power, the amount of training data available for training, decline in cost of hardware in cutting-edge algorithms and architectures have all contributed to this promise. Even though deep learning algorithms do not fully replace human specialists, they certainly help in augmenting and providing better care. So one area where this could be really useful is diagnostic imagery. This is because diagnostic imagery can be a little tricky, even for specialists. It's not straightforward. So deep learning could be really useful here. One specific area I'm working on is optical coherence tomography or OCT. It's an imaging test used by ophthalmologists to diagnose patients' retina. So the goal here is to take OCT imagery and accurately diagnose the patient's retina. I've also created a web application where you could upload an OCT image and it would provide classification. An important and commonly used technique in image recognition is CNN, or convolutional neural network. CNNs are used in image recognition, voice recognition, and natural language processing. And recently, thanks to increasing computational power and other factors, CNNs achieve excellent performance in a lot of complex visual tasks, provided enough data, of course. So we'll be using CNN to train our OCT images. This is the dataset. You can get the original dataset from this link. We have around 636 OCT images. This is, of course, limited number of data, and this presents challenges in deep learning, which we will look at. And the images are grouped into 5 classes: image-related macular degeneration, central serous retinopathy, diabetic retinopathy, macular hole, and normal. This is what the OCT images look like. This one is taken from the folder age-related macular degeneration. It doesn't make much sense for us, of course, but it's very useful for ophthalmologists. These are the technologies used: Python programming language, Jupyter Notebook to build our model, TensorFlow and Keras provide high-level APIs to process, train, and test our model. We'll be using TensorFlow JS to convert our Keras model into a JavaScript representation. This is useful for our web framework, web application, and we'll use React.js to build the web application. So moving on, first things first, we split the data into training, validation, and test sets. We'll be using 90% for training and 10% for testing, and we will use 10% of the training data for validation. And we will, of course, need to pre-process the images. The images will be loaded and decoded into an RGB grid of pixels. The pixel values will be scaled from originally 0 to 255 to an interval of 0 to 1. This is because neural networks prefer smaller values as inputs, and we then convert them into floating point tensors before being fed into the network. These are the hyperparameters I found to work well: byte size of 5, epoch 100, default learning rate of 0.01. I'm also using a popular optimizer called Adam Optimizer. So for our output, we have 5 classes. We also, in the last layer, we have a softmax activation, which gives us a probability distribution. For each class, we'll be getting a probability, and for the loss function, we'll be using sparse categorical cross entropy. We're using this because the classes are mutually exclusive. So as I've mentioned, overfitting is a problem, especially when you have a limited number of data. So this is what it looks like without using any regularization techniques. So to solve this, we of course use regularization. I've used two techniques, data augmentation and dropout. Data augmentation basically artificially increases the size of the training set by generating new realistic variants of the training set. So in the end, I was able to get 92% training accuracy, 77% validation accuracy, and 87% test accuracy. So before moving on to the code, I'll first show you the web application. This is the web application. So we just have to choose a file. This is my test folder, and these are the classes. I'll just pick one image from the normal folder. I'll just open it. Preview is over here, diagnosis here. So you can see here it properly classified it as normal with 98% probability. Let's choose another class. Let's go to AMRD. Open. So yeah, AMRD, age-related macular degeneration, 99% probability. Let's choose one other more. DR. So yeah, diabetic retinopathy. It's less certain this time, but it properly classified it, so it works well. So to show you my project folder, this is my project folder. We have the OCT classifier. This is the web application, the React application. I have my model stored in public, in the public folder right here. This is my model. This is exported by TensorFlow.js. I can access it by going to my localhost model.json. So I can access it from a web application or from a mobile application, from anything. So it's very convenient. And we have OCT images here. This is my base folder. I have my test and train files here. 10% in the test folder, 90% in the train folder. I have my original dataset here. This is the notebook, final project notebook. These are the TensorFlow.js exports. And finally, we have the OCT model. This is exported from Keras, which is an H5 extension. So moving on to the notebook. At the top, we have imports, and then we create the base directory, OCT images, and in the base directory, we create the train and test folders. And in the train and test folders, we create separate classes for both testing and training pictures, and we copy the files. As I've said, train folder contains 90% of the data, test folder contains 10%, and we copy the files here. And then moving on, we have image for pre-processing. We have image data generator, which is very useful API provided by Keras. We can rescale it here. These provide data augmentation. For example, rotation image, it randomly rotates the image here 40%. And finally, it also provides us a way to split the data into validation and training sets. So I'm using 10% for validation. And so we have train generator, validation generator, and test generator. Class mode is sparse, of course. So we have around 468 images for training, 49 for validation, and 53 for testing. This is what the shape looks like. We are rescaling it to 150 by 150. So our byte shape is 5, which are the classes. This is what the classes look like. And finally, we have the model. I've attempted some different kinds of models with different hyperparameters. I've even attempted CNN architectures like AlexNet, but they don't perform well here. I think that has to do with the fact that we don't have much data. So yeah, input shape 150 by 150, 3, which represents the RGB colors, and we have the convolutional layers and pooling layers. We also have dropout here, and finally we have softmax activation, which gives us probability for the 5 classes, and this is the loss function, the optimizer, and the optimizer. So this is the model that works well in our case, and we finally fit the model. We have after 100 tries we have 92% accuracy, training accuracy, 77% validation accuracy. So this is how our model performs. Finally, we evaluate our model against the test files. We get around 86-87% accuracy, which is pretty good. So thank you very much for listening.